This problem first came to me while setting up circular tables in rectangular rooms for wedding receptions. Everyone knows the best way to pack circles is to offset every other row by a single radius and push the rows together until they're tangent. But if you fit the circles inside of a rectangle, you end up with this empty space in the corners, and without enough circles, you'd save more space just making sure all the rows and columns are adjacent, like you'd normally stack. A similar scenario exists in 3 dimensions while trying to pack spheres into a rectangular cuboid. So the question is, for a specific number of spheres, what pattern of spheres and what side lengths create the smallest rectangular cuboid? There are 4 patterns I will decide between. The first pattern is to stack them in aligned columns and rows. The second pattern is to offset them in a single direction. The third pattern is the same as the second, except now the number of spheres in each layer alternates so that one row is shorter. The final pattern offsets the layers in 2 directions. Pattern 1 is trivial, and therefore it is equivalent to imagine 8 spheres as a cube with length 2, or as a rectangular cuboid with lengths 1, 1, and 8. If we set the diameter of the spheres equal to 1, then it's very easy to calculate the volume of the rectangular cuboid for the trivial pattern 1. Because the volume will simply be the number of spheres. For example, if the diameter of a sphere is 1 inch, then this box with 8 spheres will have a volume of 8. Patterns 2 and 3 are 2-dimensional patterns, and therefore they're always maximized in 2 dimensions, meaning that the length of one of the bases will be 1 unit long in the most efficient packing. You want to minimize the ratio of dead space along the edges to filled space in the center by lengthening the rows. And you want to make use of the height-saving pattern by maximizing the number of layers there are. But there's no benefit in this third direction. The first time any of these patterns is more efficient than the trivial pattern is at sphere count 11, where pattern number 3 has a volume of 10.9282. The trivial pattern's still best at sphere count 12 and 13. And then at 14, pattern number 2 becomes better at 13.995, but pattern number 3 is better still at 13.66. 13 is the last time that the trivial pattern is the best. 16 is the first time that pattern number 2 beats pattern number 3. 22 spheres is the first time pattern number 4 beats the trivial pattern. Up to around 100 spheres, patterns number 2 and 3 are both still very prominent, with a few pattern number 4 mixed in. And then we start seeing a lot more pattern number 4. The first time pattern 4 becomes the best of all patterns is at sphere count 52. The last time pattern 2 becomes the best of all patterns is at sphere count 160, with a base of 20 and 8 layers. The last time pattern 3 is the best of all patterns is at sphere count 168, and after that, it's all pattern 4. Using sphere count 169 as an example, we can see how sometimes for pattern 4, using the best base lengths will leave empty slots in the top layer, which means that until that layer is full, all the sphere counts will have the same volume. This trend continues into large sphere counts like 10,011 here, which has 9 empty slots. So what happens between patterns 2 and 3 in the long run? I can't think of any reason one would be better than the other. So here's a chart of sphere counts 10,000 through 10,100 for patterns 2 and 3. The flat lines indicate the volume remaining the same due to the empty spot scenarios. As you can see, there's no clear trend to whether one's better than the other. But I'm worried the numbers I'm using simply aren't large enough. The average volume difference between patterns 2 and 3 for this set of spheres is less than 1.5. But for pattern 2, sphere count 1050 and 1051, you get a jump of 7 empty slots. With larger numbers, they'd have more factors, and I hypothesized then I'd see fewer of these spikes and flat lines. So I guess if I ever get access to a supercomputer, I'll check it out. One phenomena to note is that normally pattern 4 creates a sandwich having more of the large layers than the small layers, but sometimes it has the same number of small layers as large layers. As a sample, it only happens 38 times from sphere counts 1500 to 2500, which is less than 4%. In conclusion, there's no clear winner between pattern 2 and 3 in the long run, and below 169 spheres you need to be careful how you pack them.